the rearrangement theorem, which states that each element of a group appears once and only once in a column of the group multiplication table. To see this, we consider the group multiplication table of the group C4B, and so consider a particular column that corresponds to the element mx. Now, if we look at the column, we see that each element of the group appears once and only once. For example, mx appears here in this particular cell and nowhere else in that particular column. And similarly, sigma u appears here and nowhere else in the column. And similarly, C4, C4 cube, any other element of the group. And this is true for any column in the group multiplication table, and true for any row in the group multiplication table as well. Now, we also note that the elements of a column are obtained by, for example, the elements of the column corresponding to the element mx is obtained by the multiplication of the elements of the group with mx. For example, this particular cell is obtained by the multiplication of E with mx, and similarly this cell is equal to C4 cube times mx, and this is C4 square times mx, and so on. So the elements of a column are obtained by multiplying a particular element that is labeling the column with every element of the group. Similarly, the elements in a row of the multiplication table is obtained by multiplying every element of the group with a particular element. For example, the row corresponding to this is obtained by multiplying every element E, C4, C4 square, etc. and so on with the element C4 cube of the group. And every row contains each element of the group once and only once. And similarly, every column contains each element of the group once and only once. So this, in other words, means that multiplying every element of the group with a particular element of the group reproduces all elements of the group, each appearing only once. Or in other words, multiplication of all the elements of the group with a particular element produces the group itself, but in a different order. And that's why the theorem is called the rearrangement theorem. Now we formally prove this theorem. We start out by showing that no element of the group can appear more than once in a particular column. So we consider a particular column corresponding to, say, the group element C, and then assume that there exist two cells in that column which contains the same element of the group. So that means a particular element has appeared more than once in that particular column. So we are starting with the assumption that there can be more than one element. There can be a particular element appearing more than once in a particular column, and then show that this leads to a contradiction, which would then be resolved by identifying that our initial assumption was wrong. So we first start out by assuming that a particular element, say D, appears twice in the column, and then show that this leads to a contradiction, and thereby showing that our initial assumption that a particular element can appear more than once in a column is actually wrong. So let this cell and this cell, these two cells have the same element D. So the D is appearing twice in this column, and let's say that this particular cell correspond to the column A, and this one correspond to the row A, and this correspond to the row B. So that means this element D is equal to A times C, and similarly this element here, which is also D, is equal to B times C. Or in other words, A times C is equal to B times C. Now A, B and C are elements of the group, and therefore each of them have their own inverses, and therefore C also has an inverse. Now we multiply this equation from the right hand side with C inverse. So AC times C inverse is equal to BC times C inverse. Now because the group multiplication is associative, we can first take the product of C with C inverse and then take the product of the result with A. But when we do that, we note that C times C inverse is the identity element and A times the identity element is simply A. And similarly, on the right hand side, we can first take the product of C with C inverse, but C inverse is identity, and now we take the product of that result with B. So B times E, but B times E is simply B. So this means that on the left hand side we get A and on the right hand side we get B, and A is equal to B. So that means if a particular element D appeared twice in a column, then the corresponding row elements are the same. But in a group multiplication table, every element appears only once in a row, because the row labels correspond to the elements of the group, and we only have a particular only have one row for each element. So obviously this cannot be true. This row and this row, if they are different rows, cannot be having the same element, or in other words, it cannot be that A is equal to B. So that means we have run into a contradiction, which then means that our initial assumption was wrong. So that means element D cannot appear twice in this column, and this is true for any other element as well. Okay, so now that we have established that no element of the group can appear more than once in a column of the multiplication table. Now we note that there is one row for each element of the group, and therefore the number of rows in the multiplication table, and therefore the number of rows in a particular column of the multiplication table is equal to the number of elements of the group. Or in other words, the number of cells in a column is equal to the order of the finite group. And in the first step, we have shown that no element can appear more than once in a column, and the number of cells in the column is equal to the order of the group. So that means all elements of the group should appear in the column. So which then proves the rearrangement theorem, that every column must contain each element of the group once and only once. Now consider the multiplication of a group G with a particular element X of the group, and we can write X of G is equal to X times A for all elements A of the group. So this corresponds to a particular row of the group multiplication table, because we have this corresponds to a particular row of the group multiplication table, because we are multiplying every element of the group with a particular element X of the group. Now we have already shown that in this multiplication, every element of the group appears, and it appears once and only once, and therefore this set is the same as the set of elements of G. So X times G is simply G, but the elements appearing in a different order. Now this has consequences. For example, if we have a sum given by this, where f is a function defined on the group. And assume that this function f of a will be a function onto something, and f of a plus f of b is equal to f of b plus f of a for a and b in G. For example, one may think that the function f is a mapping from the group into the set of real numbers. So in that case, this will simply be the addition of the real numbers, and the addition of real numbers is commutative. So once we do this, we can see that a sum like this is simply sum of, say, f of a1, f of a2 plus etc. up to f of ag, where a1, a2 etc. up to ag are the elements of the group G. Now, if I consider the multiplication of the group elements, say a1, a2 etc. up to ag by some other element c of the group, I will have, say, a1c, a2c etc. up to agc. Again, the same number of elements as this group, and in fact these are the same elements of the group. So if I take summation of f(ac), so this will be equal to f of a1c plus etc. up to f of agc. And now if we assume that the order of elements in the summation doesn't matter, then this second sum is the same as this sum. So there are two things. We assume that the summation, the order doesn't matter, and also the summation is over the whole group. Now in the second case also, the summation is over the whole group, because multiplying the group with a particular element of the group will reproduce all the elements of the group according to the rearrangement theorem. And if the order of elements in the summation doesn't matter, this sum will be equal to this sum. We now discuss some exercises. So we first consider this question. For a group G with a composition operation given by this dot, show that A inverse dot A is equal to E and E dot A is equal to A, and that A inverse and E are unique. The solution is the following. From the group properties, we know that for every element A of the group, there exists an inverse, which we denote as A inverse, this symbol, such that A dot A inverse is equal to E, the identity of the group. Now, A inverse is an element of the group, and therefore it also has an inverse, and which we denote by this symbol, A inverse inverse, such that A inverse dot A inverse inverse is the identity. So A inverse is an element of the group, A is an element of the group, and then we consider the product of A inverse with A. So A inverse on the left side and A on the right side, which is obviously different from this product. And our aim is to show that this is also equal to the identity. We first note that A inverse dot A is also an element of the group, because A inverse and A are elements of the group. This is called the closure property. And once that is known, we can now take the product of this equation with A inverse A from the left. So multiplying this equation on the LHS from the left with A inverse A, we get A inverse A dot A inverse dot A inverse inverse on the left hand side. And on the right hand side, I have A inverse dot A dot E. Now the right hand side is simple to evaluate because this is the identity. We know that this is equal to A inverse A. That's the property of the group, the identity of the group. Now, the LHS can be manipulated as follows. The group multiplication is associative, and therefore this product, which is the product of this element with this element and followed by the result of this product with this element. This element in fact is the product of A inverse and A inverse inverse. But then because of the associativity, I can take the product of this with this first and then take the product of the result with A inverse. So that's what we will do here. So I have A inverse and then the product of A with this. Again here we use the associative property. We can first take the product of these two and then take the product of the result with this. So that is A inverse dot A inverse inverse. But A inverse, from the definition of the inverse, is the identity. And therefore this is the identity. And therefore the product of identity with A inverse inverse is simply A inverse inverse. So this is equal to this A inverse dot A inverse inverse, which is nothing but E. So on the left hand side I have the identity E, and on the right hand side I have A inverse A. So that means identity is equal to A inverse A. But from the starting definition, I know that A dot A inverse is equal to E. Now we have proved that A inverse dot A is also E. So together we get the result A dot A inverse equal to E equal to A inverse A. Now from the definition of the identity, we have A dot E is equal to A for every element A of the group. We have to show that E dot A is also equal to A. To do that, we first note that we have A dot A inverse equal to E. Then multiplying this identity from the right with A, we get on the left hand side A dot A inverse dot A, and on the right hand side I have E dot A. And on the left hand side, using the associativity of the group multiplication, I can take the product of A inverse with A first and then take the product of that result with A. But A inverse A from equation 1.3 over here we have just proved is equal to E. But now A dot E from the definition is equal to A. So that means on the left hand side I have A and on the right hand side I have E dot A. So that means E dot A is also equal to A. So we now have A dot E is equal to A equal to E dot A. We now show that the identity is unique. So that means there is only one element E in the group that has the property that A dot E equal to A equal to E dot A for all elements A of the group. To show this, we first assume that there exists another element E dash which also has this property, and then following the group properties we will show that this element has to be equal to the element E. So assume that there exists E dash which is an element of G for which A dot E dash equal to A equal to E dash dot A for all elements A of G. So this should be true for the element E as well. So taking A to be equal to E in this equation, we get on the left hand side, so we have A equal to E, so E, and on the right hand side I have E dash dot E. But now using the property of the identity that A dot E is equal to A, with A equal to A dash, we have E dash dot E is equal to E dash. So here on the right hand side I have this equal to E dash. On the left hand side I already had E. So this means that E should be equal to E dash. Or in other words, if there exists a second element which also satisfies this property, then it definitely has to be equal to the first identity itself. Or in other words, the identity E of the group is unique. We now show that the inverse of an element is also unique. Suppose we have an element A of the group G and it has an inverse A inverse. So that A dot A inverse equal to E equal to A inverse dot A. Now assume that there exists another element B of the group which also satisfies this property, that is A dot B equal to E equal to B dot A. So that means B is also an inverse of A. And our aim is to show that this B should be exactly equal to this A inverse. To show that, we consider this part of the equation and we multiply on the right hand side with A inverse. So we have E dot A inverse, that is this on the left side, and on the right hand side I have this times A inverse, that is B dot A inverse. On the left hand side, since E is the identity, E dot A inverse is A inverse, and on the right hand side, using the associativity of the group multiplication, I can take first the product of A with A inverse and then take the product of B with the result of the first multiplication. But now A with dot A inverse is the identity and I have B here, so B dot E, but B dot E is B. So on the left hand side I have A inverse and on the right hand side I have B. Or in other words, A inverse should be equal to B. That is, if there exists a second element that satisfies this equation for a particular element A, then this B should be equal to A inverse. Otherwise, the inverse of an element A is unique. So given an A, there is a unique inverse that satisfies the property that A dot A inverse equal to E equal to A inverse dot A. Now question number 2, show that the k integers 0, 1, etc. up to k minus 1, where k is a positive integer, under the composition addition modulo k is a group. So first of all, we need to specify what the addition modulo k is, which is defined as follows. Let A and B be two positive integers. Then A dot B, which is the composition of A and B, is defined in the following way, and we write it as A plus B modulo k, which is first find A plus B, then divide it by the integer k and find the remainder of this division. So a plus b modulo k is the remainder of the division of a plus b by k. For example, if we have 2 and 3, 2 dot 3 is written as 2 plus 3 modulo k. Say for k, we will take 3. So 2 plus 3 modulo 3 is obtained as, first find 2 plus 3, which is 5. Then find the division of 5 by 3. And here the quotient is 1 and the remainder is 2. So 5 modulo 3 is 2. So 2 plus 3 modulo 3 is 5 modulo 3, which is 2. And similarly, if I have 7 and 8, and for k I have 4, 7 plus 8 modulo 4 is, 7 plus 8 is 15. So 15 modulo 4, and division of 15 by 4 will have a quotient equal to 3 and a remainder equal to 3. So 15 modulo 4 is 3. So this is how division by, addition modulo k is defined. So we need to check that the set of integers 0, 1, 2, etc. up to k minus 1 is a group under addition modulo k. So we need to check that they satisfy all the properties of the group. The first one to be checked is the closure property. So let A and B be elements of the group G. So that means A is an integer between 0 and k, and B is also an integer between 0 and k. Now A dot B is A plus B modulo k. So let us see what A plus B modulo k is. First, we note that A plus B is between, say the lowest value is 0 and 0 for A and B, and therefore their sum will also be 0. The lowest value of A plus B is 0, and the highest value is obtained by adding the highest values of A and B. The highest value of A is k minus 1, and that of B is also k minus 1. So the highest value of A plus B is in fact k minus 1 plus k minus 1, which is 2k minus 2. So I may write that A plus B is between 0 and 2k minus 1, because the smallest value is 0 and the largest value is 2k minus 2. Now, if I take the modulo k of A plus B, we have two things to consider. If A plus B is less than k, then A plus B modulo k is A plus B itself. But if A plus B is greater than k, then A plus B modulo k is A plus B minus k. Now, the maximum value of A plus B is always less than 2k, and therefore A plus B minus k is always going to be less than k. Or in other words, A plus B modulo k is always between 0 and k, including 0. So that means A plus B modulo k is also in the set 0, 1, etc. up to k minus 1. So that means if A and B are in G, then A dot B is also in G, and therefore the closure property is satisfied under this addition operation, and under this group composition operation. And the next property we need to check is the associativity. For that, we first note that A dot B, which is A plus B modulo k, as we have just seen, is equal to A plus B if A plus B is less than k, and A plus B minus k if A plus B is greater than k. greater than or equal to k. Now, we need to consider the product A dot B dot C, which is in fact A dot B plus C modulo K. And as we can see, if A plus B plus C is less than K, this is equal to A plus B plus C. And if A plus B plus C is such that K is less than or equal to A plus B plus C and is less than 2K, then this is equal to A plus B plus C minus K. However, if A plus B plus C is greater than or equal to 2K, then we have to subtract 2K from A plus B plus C. Now, we can take the product of B and C first and then take the product with A. To do that, we see that B dot C is equal to B plus C if B plus C is less than K, and B plus C minus K if K is greater than, if B plus C is greater than or equal to K. Now we can take the product with A. So A dot B dot C will now be equal to A plus B dot C modulo K. So that will be equal to B plus C plus A if B plus C plus A is less than K, and equal to B plus C plus A minus K if B plus C plus A is greater than or equal to K but less than 2K, and B plus C plus A minus 2K if B plus C plus A is greater than or equal to 2K. So that means now, since these are all integers and integer additions are commutative, we can see that the set of values given here is exactly the same as the set of values given here. And therefore, A dot B dot C as given by equation 3.2 is the same as A dot B dot C as given by equation 3.1. Or in other words, associativity is satisfied. So the third property to be checked is the existence of an identity element. And we see that 0 is the identity element, because for any other element in the set, that is a set of integers starting from 0 and stopping at k minus 1, A plus 0 modulo k. Now A plus 0 is actually any number from 0 to k minus 1 plus 0, which is the same number. So A modulo k, and therefore A modulo k is that number A itself, and therefore A, the element 0 is the identity element. That's because A dot 0 is equal to A. Now we need to show that every element has an inverse. First of all, we note that the element 0 has an inverse given by 0 itself, and that is because 0 plus 0 modulo k is equal to 0, which is the identity. So that means 0 dot 0 is equal to 0, which is the identity element. So 0 inverse is equal to 0. Now for any other element in the group other than 0, that is for element A, which is less than k and greater than 0, we see that the inverse is given by A inverse equal to k minus A, and this is because of the following. Now consider A dot A inverse with A inverse taken as k minus A, so that will be equal to A plus K minus A modulo K. But now A plus K minus K is K. So K modulo K. K modulo K is 0. The remainder of the division is 0. Now this 0 is the identity element. And therefore, for 0 we have inverse equal to 0, and for any other element A between 0 and K we have A inverse equal to K minus A. So now we have established that the group is closed under the addition operation, addition modulo K. And second, it satisfies associativity. And third, there is an identity element which is 0 itself. And fourth, every element has an inverse. Now question number 3. Obtain the group multiplication table for C4B. Now the group C4B has the following elements. The identity element, which is also equal to C4 to the power 4, C4, C4 square, C4 cube, which are rotations, and Mx, My, they are reflections about the planes, and sigma u and sigma v, they are also reflections. Certain multiplication operations can be obtained very easily. For example, C4 times C4 is C4 square, which is a rotation about an axis perpendicular to the plane and passing through the center of the square by an angle of 90 plus 90, 90 followed by 90, which is 190, or pi radians. Similarly, C4 times C4 square is equal to C4 cube, which is rotation by 3 pi by 2. And we also see that this is also equal to C4 square dot C4. Now, C4 times C4 cube is C4 to the power 4, which is rotation by 2 pi radians, which is the identity, the same as C4 cube dot C4. Similarly, C4 square dot C4 square is C4 to the power 4, which is identity again. Now, C4 square dot C4 cube is C4 to the power 5, rotation by 5 pi by 2, which may also be written as C4 to the power 4 times C4, but C4 to the power 4 is actually identity, and therefore this is also equal to 4, which is a rotation by pi by 2. Now this is also equal to C4 cube times C4 square. Now similarly, C4 cube times C4 cube is C4 to the power 6, which may be written as C4 to the power 4 times C4 square, but C4 to the power 4 is identity, and therefore identity times C4 square is equal to C4 square. Now again, from the properties of reflection, as we discussed in the class, Mx times Mx is actually identity, My times My is identity, sigma u times sigma u is identity, and sigma b times sigma b is identity. So now we start finding the products involving the remaining element and the remaining possibilities. So first we consider sigma u times C4. So the group composition is defined as follows. Consider the first operation acting on the object, and then on the result of that apply the second operation. Okay, so first we consider C4 acting on this. C4 is a rotation by pi by 2, so that A goes to this position, B goes to this position, C goes to this position, and D goes to this position. So this is equal to sigma u times B, A going to this. So So A has gone to this position, then B has gone to this position, that is this, then C has gone to this position, that is this, and D has gone to this position. Now sigma u as we have seen is a reflection about the plane given by this line. So this line is in the line of reflection, and so in the plane of reflection, and the plane is perpendicular to this square. So D and B will not change. So D and B remain in its positions, and A and C interchange. So A comes here and C goes there. So A here and C there. But now consider this A, B, C, D. Okay. Now consider the action of mx on this state A, B, C, D, which will be like this. Mx is the reflection about the plane given by this line. The plane is perpendicular to the square, and this line lies in that plane. So A goes to D and D goes to A. B goes to C and C goes to B. And that is exactly what this left hand side is. So we see that this is in fact equal to mx times A, B, C, D. And this state is the same as this state, and therefore we identify that sigma u C4 is equal to mx. Now we consider the another possibility, sigma u times C4 square, acting on this square. So C4 square is a rotation by pi radian. So A has to go to C, B has to go to this position, and C has to go to that position, and D has to go to that position. So A comes here, so that's what happened here, and B goes here, so B is here, and C goes there, C is there, and D over here. Now we have sigma u, which is again the reflection given by about a plane given by this line. C and A remain the same, and B and D gets interchanged to get this. Now consider sigma v acting on A, B, C, D, this original state. Sigma v is a reflection about a plane given by this line. So there B and D remain unchanged, A and C get interchanged. So B and D and A and C get interchanged. So that means this is exactly equal to the left hand side. So we identify that sigma u times C4 square is equal to sigma v. So the next one is sigma u times C4 cube. So C4 cube is rotation by 3 pi by 2. So A has to go to this point. Okay, so A has gone here. B goes here. So B is here. C goes here, and therefore C is here. And D goes there. So D is here. Now sigma u is reflection about this plane. So B and D remain the same, and then A and C get interchanged. But then we can see that this is exactly equal to my acting on this original state, because then if I put the line corresponding to the plane giving the reflection my, we see that A and B has to interchange, so we get B and A, and C and D has to interchange to get C and D. So we immediately see that sigma u times C4 cube is equal to my. So we can proceed like this and find all the products And finally, we can fill in all the cells in the multiplication table of C4B to get this. So we now consider exercises 2. Start with the definition of equivalence relation. So given a set X, say with elements given by A, B and so on, we can define a relation between the elements. If A and B are two elements of the set X, a relation A with suppose an A is related to B by some relation, which we denote as A relation B, and such a relation is said to be an equivalence relation provided it satisfies three properties. And the first is it is reflexive, that is A is related to A itself for every element A in the set. And the second is called symmetry of the relation, which means if A is related to B, then this also implies that B is related to A for all elements A and B of the set X. And the third property is called the transitivity. That is, if A is related to B and B is related to C, this implies that A is related to C for all elements A, B and C of the set X. And the first question in the set of exercises is that show that conjugacy is an equivalence relation. So we remember that if we have a group G, then the two elements are said to be conjugate. For example, say element A and B in the group G are said to be conjugate, in which we denote by A conjugate to B, if there exists an element C of the group G such that C inverse A C is equal to B. So that means the relation between the elements A and B is defined in the following way. A and B are related if there exists another element in the group G, which we call C, such that C inverse AC is equal to B. So our aim is to show that the conjugacy is an equivalence relation. So we need to show that this relation, the conjugacy relation, satisfies all the three properties required of an equivalence relation. First of all, for all elements A of the group, we see that A can be written as E inverse AE. That is because of the following. E inverse is equal to E, because E times E is E, and therefore E inverse is E. Then A times E is A, and E inverse is E, and therefore this will be E times A times E is A, and that is equal to A. So A can be written as E inverse AE, and E is an element of the group, or in other words, A is conjugate to itself. So we can write A is related to A via this conjugacy. So the conjugacy given by this symbol is reflexive. So now we need to show that it is symmetric as well. And suppose we have two elements A and B of the group. Now A is conjugate to B means there exists another element D such that A is equal to D inverse BD. Now multiplying this equation from the left with D and from the right with D inverse, I have on the left D A D inverse, and on the right hand side I have D, then this whole thing which is D inverse B D, and on the right side D inverse. Now group multiplication is associative, and therefore I can take first the product of D with D inverse, which is E, and then this D with D inverse, which is again D, and then take the product of B with that is B times E is B, and then take that product with this. So B with E, and that is equal to B. So what we have is B is equal to D A D inverse, because that is what we have on the left hand side. Now D is D inverse inverse. So I can write B as D inverse inverse A times D inverse, which is the same form as this with D replaced by D inverse. Now D inverse is also an element of the group. So there exists an element D inverse in the group such that B is equal to D inverse inverse A D inverse. So that means B is conjugate to A as well. So conjugacy relation is symmetric. Now we need to show that conjugacy is transitive as well. Now consider elements A, B and C of the group. Now A is conjugate to B means there exists a D such that A is equal to D inverse B D. Now B is conjugate to C means there exists another element F of the group such that B is equal to F inverse CF. Now using this equation and this equation, we can write A equal to D inverse. Now for B I use this expression. Okay, so I have A is equal to D inverse, and that's what we have written here. And for B we use this expression. So F inverse CF and then this D. But then this can be written as FD inverse, and that is because FD inverse is equal to D inverse F inverse, which we can easily prove in the following way. So FD inverse times FD should be equal to the identity. Now we see that if I replace this FD inverse by this formula, I have D inverse F inverse FD, but this is identity and E times D is D. Now D inverse times D is equal to E. So D inverse F inverse times FD is equal to E. Or in other words, FD inverse is equal to D inverse F inverse. That's what I have written here. So A is equal to FD inverse C FD. Now F and D are elements of the group G, and therefore this is some other elements of the group, element of the group by the closure property. So let us call it say H. So this is equal to H inverse C H, where H is an element of the group. That means A is conjugate to C. So A conjugate to C. So that means A conjugate to B and B conjugate to C implies A conjugate to C. So that means the conjugacy relation is transitive also. So first of all, it is reflexive, and second, it is symmetric, and third, it is transitive, and therefore this conjugacy is an equivalence relation. Question number 2. Show that an equivalence relation partitions a set X into disjoint equivalence classes, the union of which is the set X itself. So we first start with the definition of an equivalence class. An equivalence class C of a set X is a subset of X of the elements of which are equivalent to each other. So we have a set X and we have a subset A of say X, or maybe S of X, such that all elements of the subset X are equivalent to each other. And then the subset S will be called an equivalence class. So we may write it in the following way. C is an equivalence class of the set X if C is a subset of X and that A is equivalent to B for all elements A and B of the class C. Now it has the following properties. Equivalence classes are disjoint. That means if we have two different equivalence classes, different means if all the elements of the equivalence classes are not the same, in which case it will be the same, then they will not have any common element. So either two equivalence classes are the same or they have no common element. To see this, let us assume that two different classes C1 and C2 of the set X under an equivalence relation given by this symbol are not disjoint. So that means there exists at least one element of X that belongs both to C1 and C2. And we denote this element by A. So that means A is in the equivalence class C1 and A is also in the equivalence class C2. So what is the meaning of the statement that A is in the equivalence class C1? An equivalence class is a set of elements of the original set which are equivalent to all the elements of that subset C1. So if A is in C1, then it is equivalent to all elements of C1. That is, B is equivalent to A for all elements B in C1. And similarly, A is in C2 means that A is equivalent to all elements of C2. So A is equivalent to C for all C in C2. Now this is an equivalence relation and therefore the transitivity property means that B equivalent to A and A equivalent to C, which means that B is equivalent to C. And this is true for every element B of C1 and every element C of C2. So that means every element B of C1 is equivalent to every element C of C2, or in other words, every element B of C1 is an element of C2. And similarly, using the symmetry, this also means that C is equivalent to B, or in other words, every element C of C2 is equivalent to every element B of C1. Or in other words, every element of C2 is an element of C1 also. So, each element of C1 is an element of C2 and each element of C1 is an element of C1. This means the subset C1 is equal to the subset C2. But this is contradictory to the starting assumption that C1 and C2 are disjoint. C1 and C2 are the initial assumption that C1 and C2 are not the same. So what we started out with was that C1 and C2 were two different classes and it had one element, and they were not disjoint. That means there was at least one element which were common to both C1 and C2. Then it followed from the properties of equivalence relation that every element of C1 is an element of C2 and vice versa. So that would mean that C1 is equal to C2. So that means C1 and C2 are not different. They are the same, which is contrary to our assumption, initial assumption that C1 and C2 were two different sets. So which implies that if there was a common element in two different equivalent classes, say C1 and C2, then C1 is the same as C2. Otherwise, there cannot be no common element. So that means if two equivalence classes are different, if they are not the same, then they must be disjoint. Now, the second property that these equivalent classes have is that every element of X belongs exactly to one class of X under this equivalence relation. And this is because of the following. For every element A of the set X, A is reflexive, so the relation is reflexive and therefore A is related to itself. And therefore it belongs to at least one class, the class that involves that particular element. Now, since the classes are disjoint, an element in a particular class cannot be in another class. So that means every element will belong to one class, at least one class, but then it can belong to only one of those equivalence classes because the different classes would be disjoint. Therefore, every element of X belongs to exactly one class of X under an equivalence relation. So that means if we take the union of all classes of X, then we will get all the elements of the set X. Therefore, the union of all equivalence classes is the set X itself.